Today is the first class on neural networks, which is what the rest of the course is going to be about. I'm just going to take the next few minutes to talk about kind of a zoomed out view of what we've been doing in the course and where neural networks fits into that. So at the beginning of the course that I'm calling Part 1, we talked about directly learning maps or transformations from the feature vector x to the target value y that we were after. And that was, for example, decision trees. Then in Part 3, we talked about linear models, and we had this idea of change of basis, which is that we can do something to transform our features and maybe get them to be better features, and then we'll get better performance. And we also talked about feature selection, which is part of this as well. Then in Part 4, which was what we just finished, we talked about latent factor models and PCA, and we can draw this kind of picture of PCA, which is that x and z are related by a matrix multiplication. We were kind of writing x as some matrix times z, but you could also write z as some matrix times x. And that was just W transpose, actually, when we were doing orthogonal PCA. And so we can think of, we have some x vector represented as a bunch of circles, where each circle is a number. So all those circles represent a vector. And then we have our z vector on top, which is a bunch of circles. And the transformation is a matrix multiplication, which means the definition of a matrix multiplication is that each z is a weighted sum of the x's, and those weights are the entries of the matrix. And so all those arrows coming into a particular z are saying all of those x's are kind of feeding into that z in a weighted sum, and then all the arrows basically are represented by the matrix. So we could use PCA for supervised learning by saying, let's first do this to get new features and then do some standard supervised learning using the new features to predict our y values. And so what we're going to do with neural networks, one way of looking at it, there's several ways of looking at it, is that we are going to simultaneously learn the features, which if you want you can think of as the PCA matrix, and the supervised learning part. So it's kind of like we're doing PCA to get a new feature vector z, and then we're doing linear regression on top of that, and that gives us v. And if we're doing linear regression on top of it, I can use the same arrow diagram for the upper layer and say my y that I'm predicting is just another weighted sum of those z values, because that's what linear regression is. It's just a weighted sum of the inputs. So in pictures, beginning of the course, I have the features. Let me do something with them. And then, well, we talked about clustering. And then we talked about change of basis. So I'll just come up with something. I think this will be a good idea. Do that, and then do supervised learning. We talked about PCA. And then maybe that's going to give us good features, and we could use those for supervised learning. And finally, what we're going to talk about for the rest of the course. So the intuition here is that if we're going to be doing supervised learning anyways, and we'll be talking about supervised learning for the rest of the course, then we should keep that in mind when we're trying to figure out what the features are. Let's allow the y values to inform us what a good feature transformation is, instead of just figuring that out in an unsupervised way and then only using the y values later. So you can think of it as learning features and a linear regression and a logistic regression at the same time. Okay, that's a very high-level, big picture way of thinking about it. So let's go into some details. Or any questions on this, I guess, before I proceed? Okay. So the notation we're going to use, at least for now, is that we have our x and y, and then w is going to be this first matrix, which takes us from our original features to these new features. And then we're going to use v to mean the coefficients of our linear regression, our logistic regression, our linear model at the end. And we'll use z to talk about our features that we're learning. So these kinds of pictures, people love to draw these kinds of pictures when they talk about neural networks. So it's useful for you to be able to interpret them even if they're not going to directly impact code that you're going to write or something like that. It's good to have a fluency with these kind of pictures. So just to reiterate, each circle contains a number. So a row of circles is a vector. Each line is also a number, each arrow. But it's a parameter rather than a feature, and it's an element of a matrix that you're learning. And when you have arrows from everything in this row to everything in that row, that's exactly a matrix. In this case, well, a k by d matrix. And then each arrow has a little number, which is the element of the matrix, which says for z5, how much of x3 am I putting in here? That's the 5,3 element, or 3,5. Okay, so the way I've been making it sound is, okay, I'll just use a linear latent factor model and then linear regression. That's sort of sounds like how I've been pitching it. Z is w times x, y is v times z. So the whole loss is going to look something like this. Here on the left, we have the linear regression loss, the least squares loss, with z as our features. But we're saying, well, z came from w times x, so I'll just replace that in. And now here's our loss over here. But if we re-parenthesize things, we see that v times w is just some vector v that we're learning times some matrix w that we're learning is just some other vector. Which means I could rewrite the whole thing as just w transpose x. So to say this in words, if I say I'm going to simultaneously learn this matrix that gets me from original features to new features, and this vector that gets me from new features to my prediction, and this is my whole model, it's kind of pointless to do the first step because it's actually mathematically equivalent to just doing linear regression to begin with. I'm not getting anything by multiplying that by that matrix. I'm just writing down a linear transformation in a more complicated way without gaining anything. So the point of this slide is that the way I've described things so far doesn't actually make sense. It's just linear regression, but with a whole bunch of extra complications. Okay, I think this is not a particularly straightforward slide, but we can also come back to it. So here's the strategy to deal with this. If we're just going to take a linear function and then another linear function and compose them, and that's just pointless because it's still a linear function, then we're going to introduce something about the system that is not linear. And we actually call this the nonlinearity in neural networks. And typically, the way this is done is every element of z gets passed through some one-dimensional nonlinear function. So for example, a common choice, or formerly popular choice especially, is the sigmoid function. that says I'm going to do my first step, multiply x by a matrix, get z, but then before I immediately take z and do linear regression, let me do this thing to each z value separately. Excuse me. And then let me do linear regression. And now the whole thing is not just doing linear regression anymore, it's doing something more complicated. Okay, so what I've just described, so this nonlinearity h, and it's also called an activation function. There's just a whole bunch of terminology we have for neural networks, nonlinear thing, nonlinearity, activation function, they're all the same thing. And what I've described here is an example of a neural network. So we need to generalize this a little bit more, but what I've described would already be called a neural network, also called a multi-layer perceptron. So, okay, well, we can do this first.
Mike?
Yes,
so why does making something nonlinear increase its flexibility?
Why does making something nonlinear increase its flexibility? Let me come back to that in a minute, yeah. But yeah, I want to answer that with the Jupyter notebook. So going back to these pictures, these are the same pictures I showed you before. This third one is kind of this not quite making sense idea that I just do a matrix multiplication and then another matrix multiplication. And this thing on the far right is what we've just talked about. We've added this extra step where each z value gets this h function applied to it. Edwin.
Could we go back to the previous slide?
Can we go back to the previous slide? Yes.
So the h transformation is slightly different than what we did before, right? Before we were transforming w times x, that's actually the y value to a probability.
Yeah, right, okay. So Edwin is saying, hey, I've seen this sigmoid function before when we were transforming the raw output of logistic regression into a probability. So yes, that's different from what we're doing here. You could still do that. So if you were doing classification with this neural network, you could take the final output, which is a single number, and pass it through another sigmoid and interpret it as a probability. But we're not using it because we want to interpret these things as probabilities. We're really using it because just any function that's nonlinear, I mean, some might work better than others, but any function that's nonlinear will solve this problem we had, that by just doing more linear stuff, the whole thing is still linear. So I'm going to deviate from my plan a little bit, and I'm just going to head over to the Jupyter notebook, I think. I'll be a little more patient. Okay. So, so what you can do with this is everything I just described, you can repeat it multiple times. So here's the first part. You get some feature transformation. You can then do another round of this, multiply by a matrix, and then do the h function, and then get the final value. So each repeat of this is called a layer. And then this would be this neural network on the right has one more layer than the neural network on the left. Excuse me. And what we're doing is we're saying, I start with my original features, I transform them, then I transform them again, and then I finally get to the output. And we're still hanging on to Fed's question of why is this giving us more flexibility, which we can get to in Jupyter. But that's what, so when we say deep, if you've heard the word deep learning, it means many, many of these layers stacked on top of each other. So it's kind of a recursive operation. Do this thing over and over again to the output, and then eventually when you're done, you do your linear or logistic regression. And so you could think about this when you have more and more layers as doing crazier and crazier stuff to get your features, and then still just doing linear regression at the end.
Do we still have the constraint of having k needing less than d?
Do we still have the constraint of needing k to be less than d? Good point. Okay. No, we don't have that constraint. And in fact, we get to choose k separately for each layer. So we're actually getting ourselves a whole lot of hyperparameters here, because it's a hyperparameter to decide how many layers you want. And then once you decide that, you also get to decide the value of k for each layer. Okay. Okay, so if we want to write this mathematically, it has this very weird recursive kind of flavor that I was mentioning, that the linear model is just w times x, and then one hidden layer is, well, first I'm going to transform x by multiplying it by this matrix and doing the nonlinear thing, and then I'll do linear regression. Or I can have two hidden layers by doing this again, and that w1 and w2 do not have to be the same matrix. They don't even have to be the same size of matrix. You can go from a 10-dimensional space to a 20-dimensional space to a 5-dimensional space to one number or whatever it is that you want to do. I think this is a useful place to pause for a couple of minutes. So, questions about any of this, but in particular, what is the diagram saying? What are the equations saying? And why are they saying the same thing? Yeah, what's your name? Yu Chen?
How do people choose what roles each layer does?
What roles? What do you mean by that?
For alpha 0, they have a certain layer that looks at policies, and then lower layer that looks at positioning and
Okay, that's well, you're way ahead of us here. So Yu Chen was asking about alpha 0. Give us a few days. This is just the very first time we're seeing neural networks. There's many aspects of that system that are beyond what we're going to do today, and also way beyond what we're going to do in the course. Yeah, but for now, we don't necessarily have to think of each layer having a particular role. Some people like to think about it that way and sometimes try to show interesting pictures about that. But I'm fine if you just want to think about it as some crazy feature transformation followed by linear regression, at least for today. Connor.
Do we have to apply the same function at each layer?
Do we have to apply the same function at each layer? So do you mean the activation function, H?
Yeah.
We don't have to.
Okay.
If we allow ourselves not to, that's even more hyperparameters. So at each layer, we actually have a whole bunch of hyperparameters. So you can imagine, way more so than any other part in this course, the number of hyperparameters is going to get to be huge here. Like we're used to having, you got to pick lambda for regularization, excuse me, or a couple hyperparameters, but here we could easily have 20, 30 hyperparameters just by the things we've been describing, and there's much more coming next class. Godwin.
What's the benefit of having multiple layers?
What's the benefit of having multiple layers? Yeah. So there are some arguments about this because the more layers you have, the more complex the model is. And we've talked about complexity throughout the whole course. So we could have deeper decision trees that were more complex but overfit more, or shallower decision trees. We could have a smaller sigma for our RBF features or a larger one. So that same fundamental trade-off we've been dealing with, it's present here as well. The deeper the network, the more complex the thing is. And a sort of proxy for that is how many parameters are we actually learning, right? And the deeper it is, the more parameters we have, because each layer has more parameters that we get to optimize. The thing is, you can also get yourself a lot of parameters and thus a lot of complexity by making it really wide. So you can just have ridiculously large k in the first layer, and then you also have a very excuse me, large number of parameters. So there are some arguments about what is better, deep networks versus wide networks. I think the important point for us here is that both of those things control the complexity and the fundamental trade-off. And the deeper we go and the wider we go, the more parameters we have, the more complex the model is. And next class we'll talk a lot about regularization and how to not overfit like crazy. Forget your name.
Vanessa.
Vanessa.
I could have missed this, but is every Z taking in all of the features, or are we leaving one out? Because I think we had a problem in ensembling where if we used all of the features for every single one, you'd get the same answer for each.
Okay, the question is, are we using all the features for every single Z at the next layer? And we are. So that's also true in PCA, I guess. So if you take a particular Z vector in PCA and say, where did each element in that came from? It was some linear combination of all the original features because it was some matrix multiplication. So yes, for the moment, for today, and that'll change next week, this thing is kind of dense with arrows. Like there's an arrow from every X to every Z. And again, every arrow is a number that we get to learn because it's an element of a matrix. So there isn't a problem like the one you described. The main problem is just you have a lot of parameters, so you have to be careful about overfitting. Okay, we have this issue of adding a bias variable that we've had with all our linear models. And I don't have much to say here other than it's the same thing. We had a bias in linear regression. We're going to have a bias here, except we're going to have these not just at the very last layer, but all the way through. So it's just adding a few more parameters to the mix. And we can, again, do the column of ones type thing if we want. So the punchline here is we have one extra parameter per Z variable so every Z is actually a weighted sum of all the X's plus some bias or intercept term that we're also learning, which is exactly what it was with linear regression and logistic regression and all that stuff. So this is not super fundamental, but it's good to remember. And you can draw it. So one way of drawing it is like this. We've never drawn it like this before because we only introduced these types of diagrams today, but we can revisit what we did a month ago when we added a bias to linear regression and say this is what we were doing. We're adding an extra feature that's always 1, and now that feature gets its own arrow to the output, and that arrow is a parameter that we're going to learn, and it's exactly the parameter we've been calling beta. It gets multiplied by 1, which is just itself, and added to all the other stuff that's feeding into the output. So we can just spice up our diagram a little bit with all these biases. Okay, this is the moment I was waiting for. So let's get ourselves over here. Okay, so I wanted to present another way of thinking about neural networks. Think about regression in 1D. So here's some points. It's always more dramatic if the outputs aren't there yet. Okay. So here's a linear fit through some points. Here's a quadratic fit through some points. I just picked the coefficients arbitrarily. When we talk about these things, like as humans, we say those are both polynomials, or those are both polynomial fits. But they're not the same function, right? The first one is a linear function, second one's a quadratic function. But there's some human notion that combines them all in such a way that we have a word for them, like polynomials. That has come out to be useful, right? So I would call this a family of different functions or models. And each member of the family is a little bit different and has a different number of parameters. Like the linear member has 2 parameters, the slope and intercept. The quadratic has 3 parameters. The cubic has 4 parameters. So there are a whole bunch of functions that are grouped together by a similar theme. We have a word for them to describe them, but each member has maybe different numbers of parameters. And then within quadratics, of course, I can change those parameters, and I can get many different types of quadratics. So there's kind of this hierarchy of polynomials, linear, quadratic, cubic, etc. And then within linear, there's infinitely many lines, and within quadratic, there's infinitely many parabolas. And those are kind of the next level of the hierarchy. So I think it's important to realize that the word neural network is just talking about a family of functions like polynomials. It's nothing more than a bunch of different mathematical functions that are really weird looking, but they're just a bunch of functions, and we use a word, neural networks, to talk about all of them because they're very similar. And again, the different members of the neural network family have different numbers of parameters, like linear, quadratic, etc. Because, for example, if we have more layers, now I have more parameters. If we have bigger layers, I have more parameters. But we have a word for them because they all sort of follow the same theme. And with polynomial, the theme was I'm getting a higher and higher degree of these, some x raised to some power, and I'm changing that power. And here the theme is something slightly different. It's take a bunch of numbers, multiply by some matrix, and then do this nonlinear thing, and then multiply by another matrix, and then do this nonlinear thing, and eventually be done with it and multiply by some final matrix or vector. But it's just a function, right? It's just a function from d numbers to one number, or sometimes you don't output one number, you output more than one. But they're just a bunch of functions from some space of numbers to some other space of numbers. Okay, so here's some code. I just want to show you this code. I mean, it's so trivial that it's almost not worth showing, but that's exactly why I want to show it. So here is a Python function that computes the mathematical function called a neural network. There it is. You give it x, w, and f, and f being the nonlinearity. I guess, sorry for not calling it h. I should be more consistent here. And I can just pick some values, and that's really it. Done. So in this case, W was size 2 by 5. And when you see the size of these matrices, the second number is like the input size, and the first number is like the output size. So 2 by 5 matrix means I'm going from 5 numbers to 2 numbers. So this is a bit different from the neural network we saw in the slides, because all the ones we saw in the slides always ended up with a single number. But this is also a valid neural network, and we'll talk about why this is useful as well. So here's a slightly fancier piece of code that says, you give me W is now a list of matrices, I mean like a Python list, and I'm going to iterate through that Python list, get all the matrices, and then I'm going to take X, and we were calling them X and Z in the slides, but I'll just keep calling it X and overwriting X, keep overwriting it. But I'm just doing that thing with the first matrix in the list, and then doing that thing with the second matrix in the list. And it's probably a little easier to think of this recursively, but I'd rather implement it as a loop. But you're really kind of recursively applying the same thing over and over again. And now we can look at the W's, and we can figure out what should be coming out. So W1 is 2 by 5. If this was 2 by 6, it would just throw an error, because I can't multiply a vector of length 5 with a 2 by 6 matrix. So there's the error. W is 2 by 5, so now I'm getting 2 numbers. Now this number has to be a 2. That's no longer a number I'm free to choose, because they have to align with the previous layer. And so by looking at this and seeing this 1 here, I'm expecting just a single number to come out. Yeah. What's your name?
Arthur.
Arthur?
It's just like in the first line, it's still F.
Oh, thanks. Thanks. That's the kind of bug that happens in Jupyter only. That wouldn't normally work. Yeah, okay, thanks.
Do you think you could draw the network, or is that too deep, too much?
Sure, I can draw this. So you start with 5. And then we have a 2 by 5 matrix. So we're going to 2. And then we have 1, and then there's just all the arrows. I probably missed some, but yeah, something like that.
Because the W's are the edges.
The W's are the edges, exactly. They are the parameters that we are actually going to learn. We're going to do gradient descent with respect to them, just like with PCA and linear regression and all these other things. And yes, in the slides before it showed the H, application of H as like a separate layer in the picture, but that's not actually standard. So it's just kind of implied that this matrix multiplication happens and then H happens, but you don't usually draw it. Okay. Any other questions about this? Okay. So here's an important question. How many parameters do we have? I'm using D sub whatever to be the number, the size of the layers. We're also saying K, K1, K2, but whatever you want to call it. Number of parameters are basically the sizes of these matrices. So if my layer sizes are D0, D1, D2, or however you want to call them, maybe K, D, then K1, then K2. Maybe that's how we would say it in the course. Number of parameters is the size of the matrices. So we have a D0 by D1 matrix and then a D1 by D2 matrix, just like we had in the code above. Here we have 5, 2, 1. So the size of the matrices are 5 by 2 and 2 by 1. So this tells us how many parameters we have, where I'm using L to be the total number of layers. Or if you want to be careful and account for the biases, it's just slightly different. But the point of that is a lot of parameters, right? So if I have 10,000 features coming in, and then 10,000 features, and then another 10,000, I already have 10 to the 8 numbers in each matrix and a bunch of those, and I can immediately get into a lot of parameters. So we're dealing with way more parameters than we have dealt with previously in the course. And all of, not all, but a lot of next lecture is going to be about regularization, because with this much many parameters, this much flexibility to learn different functions, we can potentially overfit pretty seriously. And it also makes optimization hard and complicated. Okay. So this part is where I feel like I can finally try to answer Fed's question from the beginning about what is the point of all this. So here's some 1D data set. And well, I could fit a linear regression on this, and you can imagine what it's going to look like, right? So this is scikit-learn's implementation of a neural network. It's called MLP. I mentioned before, these are sometimes called multi-layer perceptrons, so that's what MLP is saying. And I'm going to fit this thing. And then I'm just going to plot the results. And I get this kind of curvy looking thing. So I guess that kind of answers your question in the sense that a linear model couldn't do this. But this function that I've been talking about before, it's a mathematical function. It's not a linear function, right? It's just some weird function. And we're only looking at it in 1D here. But in many dimensions, it's weirder looking. But we can pick whatever W's we want. That's what fit is doing, right? That's what training is doing. So, but the space of possible functions that we could get at by picking different W's is a whole bunch of weird things, right? That are not linear, whereas the space of possible linear models is just a line or a different line. So I would say the more mess you add to this, meaning like the more layers and the bigger layers, the bigger the space of possible functions you could have, which increases the chance that the one you actually want is one of the possible ones. And there's this big question of one you actually want because of overfitting. So you have to be very careful, because if this can fit pretty much any function, then if we're not careful about regularization, we'll just get zero training error and have bad models, right? So we do need to be careful about that, but does that answer your question about adding flexibility?
Yeah.
So you can get inside this thing and ask it for the weights and stuff, and you'll just see this is, I think, a default one hidden layer, meaning one. The words hidden and visible, you'll encounter those. So visible is like the stuff you see, meaning the features and the data, and then hidden refers to all the stuff in the middle. So I think this is one hidden layer by default, which means two matrices, and you can actually get those matrices out and see what they are. Okay, so this is my favorite part, and we have time, so that's good. I think it's very helpful in building intuition to just look at what do these functions look like with random w's, because as I said, they're just functions, right? And we can pick w randomly and just sample some of these functions and see what they look like. My previous version of this, I had some home-cooked neural net code, but I switched to the scikit-learn one, and I wasn't able to get it to do my bidding entirely, in the sense that it wouldn't let me predict before calling fit. So my hack here was just to set the number of iterations to 1, which means it's not really doing a good job of fitting. It's like roughly just using the original randomly picked weights. Okay, so, and I'm just fitting some nonsense data. It's just one data point at 0, 0. That's it. Yeah, we can ignore the warnings. It's fine. It's just saying it hasn't converged. Of course it hasn't converged because I only allowed it to do one iteration. Okay, so this is a line. It's a line because I set hidden layer sizes to an empty tuple, which means there are no hidden layers. So this thing is just linear regression. I don't even have this layer. I just have a vector going from my one input to, or it's not even a vector, I guess just a number. But I can keep rerunning this. Oh, why is it not randomly initializing? That's sad. Oh, there we go. I'll get different lines. So, yeah. Here's what I can do now. I can put something in here. So this is saying, what I'm doing here is I'm going from 1 to 10 to 1. Because I have one input feature, I have one output, and then I say hidden layer size 10. And we can just look at what these functions look like. So this is just basically functions that can be represented by a neural network. And I can just keep doing this, and I'll get different functions. And it's just nice to play around with and see what these functions actually are, right? And this is all with the sigmoid nonlinearity, but there's other things that we're going to talk about later, other choices of h. And if I change my choice of h to something else, then I get other kinds of looking functions, like this sort of piecewise linear-esque thing. So this is all in the big family of neural networks, right? But there's a huge amount of hyperparameters that I can set. So again, the main reason I'm showing this to you is to just keep reiterating the fact that they're just functions. They're complicated only because they're pretty weird looking functions, and they're a little hard to write down because of this recursive nature. So So we can do more layers. I don't know what's going to happen exactly, but probably just look a little crazier. Yeah. Okay. So that was that. I have the same demo for d equals 2. So this was 1 to a bunch of stuff. I should have said that this tuple in Python contains the sizes of the hidden layers. So if there's 3 numbers in that tuple, it means 3 hidden layers. So I was going now from 1 to 10 to 100 to 10 to 1. That's what that means. Okay, Gareth and then Sasha.
So it looked like when we had a single layer of the sigmoid function that the overall picture of the fit looked like a sigmoid function as well. They make some general statement about that, like.
Can I make a general statement about the fact that the overall function looked like a sigmoid?
When your activation function is also sigmoid.
Yeah, so definitely the activation function is going to change the type of functions I get, and the sigmoid is smooth, and the stuff I'm going to get out is smooth. But we have to be very careful because the sigmoid is monotonic, right? But if I have a bunch of layers here, well, that's not very satisfying. I'm afraid scikit-learn is not really initializing randomly. Anyways, I can get functions that are not monotonic out of this thing with the sigmoid. So I'm just thinking of what scikit-learn is doing. It's probably regularizing and all kinds of stuff that I don't want. So I guess, sort of. I don't think I can make a strong statement about intuition about what these functions are going to look like, except that the activation function, like the ReLU, the other activation function, is not smooth and the output was not smooth. That's basically the best I can do. But I think it's hard to have an intuition for what the functions actually look like. Sasha?
I was just wondering if you can explain again how you go to the wider layer from your input.
How do I go to a wider layer? So let me scroll up here. So for example here, my input had 5 numbers in it. I could pick this number to be whatever I want, as long as they match each other. So if I write the code like this, it says I'm multiplying a 5 vector by a 100 by 5 matrix. The result is going to be 100 numbers. Because that's what happens when I...
And it's just finding a different, is that a different basis for our...
It's kind of like a different basis. It's a different set of operations that I'm doing on my original thing, on my input to get my output. And we can kind of think of it if we want, like that was the original pitch of the lecture. We're learning a basis and then doing linear regression. And that's one way you can think about it. Or you can think about it as we're just learning crazy functions of this particular form and not really think about it in 2 steps. They're both useful perspectives to keep in mind. But here, this is doing what you asked about, right? This is taking 5 numbers, hitting it with that matrix, it becomes 100 numbers, hitting it with the next matrix, it becomes a single number. Okay, interesting. Yeah, we got 1 because this is a sigmoid. Okay. So here's d equals 2, meaning the input is of size 2. And let me again use no hidden layers. So this is just linear regression with 2 numbers becoming 1 number. And it looks like we've basically looked at these types of pictures a month ago. Like this is what linear regression is with 2 features. It's a plane. And we can run it again and get a different plane. Again, these are just random-ish weights. So this is a neural network with 0 hidden layers. In other words, it's just linear regression going from 2 numbers to 1 number. But now the fun kind of starts because we can see what these things actually are going to look like. So here's, it's hard for me to interpret that, coming back to Garrett's question. Like this is going from 2 numbers to 10 numbers to 1 number with a certain type of nonlinearity. And can I characterize what these functions are going to look like? Sort of. A little bit. Yeah, a little bit, but it's complicated. Okay.
Is this using ReLU or?
Yeah, this is using ReLU, which we haven't talked about. I think that's the default. And sigmoid, which they're calling logistic, is non-default. Yeah, so here's some sigmoid thing, and then we can spice this up again. Oh, it just flattened out. It's because it's saturating. It's the same problem that we had above. The ReLUs will be more fun. Yeah. So all I'm wanting you really to take away from this is these are the type of functions we can learn. And the more layers we have, the crazier the functions are. And the bigger the layers are, the crazier the functions are. And all of next class, we're going to have to talk about the training procedure. What are we going to do? How are we going to fit the thing? But this is what the functions actually look like. So we can talk about software later. That's fine. Just have a couple of slides left. So there's an interesting history to this field. So deep learning basically means the same thing as neural networks. As I said, deep refers to more layers. So people were super optimistic about this in the 50s and 60s, and famously at MIT, a researcher assigned some students the project of, I don't remember what the words were, but take a camera, hook it up to the computer, and have the computer describe what's in the image or something like that, which turned out isn't really quite solved now. So definitely not a 5-person summer project in the 1960s. But that just shows you how much optimism there was. Some would say we're currently in that collective state of mind again now in the late 2010s, and that there's a lot of buzz about deep learning, and I guess it remains to be seen what will happen. But yeah, there was a lot of progress, but there's this notion of AI winter where people also became disillusioned with AI, and AI became like not the right word to put in your grant proposal. And now it is, of course. Yes, you should say, no matter what you do, you should say it's machine learning. But and SVMs were also super popular. They came out in the 90s. So what happened more recently is that suddenly there was just this huge comeback of deep learning and just took over and started dominating a whole bunch of fields and competitions relatively suddenly. And the people think the reason why this happened was partly some new tricks that we're going to talk about next class, partly just way more data, and a lot of it was just way more computing power, and GPUs in particular, I think I mentioned before, play a big part in that, and they do essentially parallel processing that can really speed up this computation. So there's huge improvements in speech recognition. Your phone, if it has Siri or Android or whatever, is using this stuff to figure out what you're saying. Computer vision has been blown up by deep learning, like really blown up, like way more progress in a few years than was made in like decades before that kind of thing. Big revolutions quite suddenly, and that's why there's so much excitement about this stuff. Finally, there's just a lot of vocabulary. So I think, artificial neural net is the same as neural net, is the same as neural network, is pretty much the same thing as deep learning-ish. Those are abbreviations: neural net, artificial neural net. CNN is convolutional neural network that we'll talk about next week. Units, neurons, and activations all refer to these numbers. They just have those weird names, but they are the numbers in the intermediate layers. Hidden and visible I talked about, and activation function and nonlinearity I talked about. So that's it for today. We talked about neural networks, a point of view that they're simultaneously learning the basis and the weights, or the point of view that they're just a function. We talked about the sigmoid as one possibility, deep learning, and really good performance, and we'll get into a bunch more detail next week. Have a good